Okay, so in this video, we're going to discuss the last part of our topic in electrical circuit variables and elements. So we're going to discuss circuit elements, linearity, and short and open circuit. Shown here are the circuit elements that are commonly found in a circuit. So these are subdivided into two groups. So we have um, the active elements. And here we have the what we call the passive elements. So the active elements are actually the sources. So it could be a voltage source or a current source. Now, under the active elements, they are further subdivided into independent and dependent sources. So, what do you mean by independent source? So, these are the independent sources. So independent sources are circuit elements that provide their own energy. So they produce their own energy. So a good example of that is the battery that we usually use every day. While the dependent sources, so this is a dependent voltage source and this one is a dependent current source. Uh, they derive their energy from some other elements in the circuit. So in dependent sources, they are classified further under different types. So we have the voltage controlled voltage source, current controlled voltage source, and voltage controlled current source. And the last is the current controlled current source. So um, it has to be noted that these are also the symbols used on these elements. So for an independent voltage or current source, so these are the symbols, and we use a circle to denote independent sources, while for dependent sources we use a diamond shape source. So for resistance, this is the symbol. This is for the inductor or inductance, and this one is for the capacitor or the capacitance. Now let's go to linearity. A circuit element is linear if it satisfies two conditions. So one is the homogeneity, and the other one is the additivity condition. So let's discuss what do you mean by these conditions. So for homogeneity, let's say we have a simple circuit. So we have a resistance that is powered by a voltage source V sub S. By Ohm's law, we know that the current is given by this, so it's a ratio of V sub S over R. So let's assign that to the variable I sub S. So in this illustration, a voltage source produces a voltage source V sub S will produce a current I sub S. Now let's say I increase the voltage by a factor of K. So we have the same circuit, but we just increase the voltage by a factor K. Again, by Ohm's law, we know that I there would be KB sub S over R. And you'll notice that this one here is your I sub S, the one that we got here. So I would be equals to K times I sub S. So we therefore say that given a voltage K times V sub S, it will produce a current of K I sub S. So this concludes that if we multiply the driving voltage by factor K, we will produce a response, or in this case, a current, which is also uh, will also have a factor K in in its final result. So therefore, we can say that the resistance satisfies the homogeneity property. Now for additivity, let's say we have this circuit and we have a resistance again, and this time it is excited by two voltage sources, two independent voltage sources that are connected in series. And again, by Ohm's law, we know that the current would be given by this, and we can actually separate this into two terms, so V sub 1 over R and V sub 2 over R. Now let's say I am going to separate the sources, or will break the circuit and separate the two sources such that I now have two circuits with a voltage V sub 1. One of the circuit has a voltage V sub 1 and the other one has V sub 2. Now if I'm going to compute for the current, I will get this. And for I sub 2 on the other circuit, I will get this. Now if I'm going to add the two currents like that, I will get something like this. And take note that this one is really this one also. So therefore, we conclude that in this circuit, the total response, or the current in this case, is really the individual response if the voltage sources are separated. So in this case, the response here is I sub 1. If we have V sub 1 as the source, here we have I sub 2 if the voltage is V sub 2. And if we're going to sum up the responses, what we get is the same as the original circuit. So therefore, we can say that the resistance also satisfies the additivity property. And therefore, a resistance in our example is a linear element. In practical applications, a very good example of a linear element is the resistor. So shown here is the resistor along with its symbol. So if we're going to plot uh, the relationship between, let's say, the voltage across the resistor and the current that flows to the resistor, you would get a, a plot that looks something like this. So for a certain range of the current and voltage, you will get a linear result. But on extreme cases, uh, it's not anymore linear and it becomes nonlinear, in fact. Now, this happens if the resistor temperature is changing to beyond its limits. So, a resistor, therefore, is only linear for a certain range of temperature, and beyond that, it becomes nonlinear. Now, there are some elements that are nonlinear, and one example of this is the diode. So a diode looks something like this. So we have, if you have seen a diode, so this is the anode part, the anode side, and this one is the cathode. And the symbol looks like this, looks something like that. So if we're going to plot the voltage and the current relationship of the diode, so let's say we plot it. So let's say this is the current through the diode, and this is the voltage. You'll get a curve that looks something like this, something like that. So there is no uh, practical linear part on the curve of the diode, so therefore this diode is classified as a nonlinear element. Now let's go to switches. So a practical circuit must have a switch. Switches are used to open or close a circuit. So what we mean by open is that if current flows and we open the switch, the current stops. If we close the switch, the current continues. So ideally, switches acts like a short circuit, and yes, it is a short circuit when it is closed, and it is an open circuit when it is open. A common symbol of a switch looks something like this. So we call that the single pole, single through switch. Now, in this symbol here, in which we have an arrow and time equals 0, uh, this means this is a switch that is initially open, and when time t equals 0 hits or arrives, that switch is closed. Conversely, for this symbol, the switch is initially closed, and when time becomes t equals 0, the switch is open. So that is the interpretation of these symbols here. A switch is like a resistor with two states. If the switch is closed, its resistance is 0, but when it's open, its resistance is infinity. So let me explain this statement. So let's say I have a source here, an independent voltage source, and connected to a resistance. So let's say this is a resistance. And let me put a switch, an SPDT switch. Okay, so let's use a different color. Go like that. So let's say the resistance is R. So this is our voltage here. If this switch is open, so current cannot flow. So there's no current here. So I will be equals to 0. Now, let me replace the switch by a resistance. So I have another illustration here, and let us replace the switch by a resistance. And this is our resistor here, and let's connect it. Okay. Now, so since this switch is open, that means we're assuming that the resistance of this is actually infinity. This one is infinity. So this is the resistance of the switch. So here is the resistance of the resistor. Now, what happens to the current? So if we apply Ohm's law, current there would be equals to the voltage plus divided by R plus infinity. And indeed, we will get here a value of 0, which is the same as this one. And therefore, we can say that if the switch is open, the behavior of the switch is like a resistance that has a value of infinity. Now, if we close the switch, so we close the switch, and therefore we will get an I that is equals to V divided by R plus whatever the resistance of that switch. Uh, okay, so let's say the resistance of the switch is R sub S. And let me again replace that switch by a resistor here. And since it is already closed, we have a resistance of the switch becomes 0. And therefore, if I'm going to compute for the current, I now have V divided by R plus 0, and this is really just V over R, something like that. So, well, in this first illustration, switches has practically no resistance, so this one really is a 0, and therefore I here also is V over R. So that matches with that, and therefore we can conclude that if the switch is closed, it is like a resistance that has a value of 0. Okay, so in this last slide, I just put it here a practice problem where you can apply your knowledge that we have already discussed, and I encourage you to go over this and find an answer for this problem. So that's it for this video and for this topic on electrical elements and variables. On our next topic, we will be discussing resistive elements. We will go into the basic analysis of resistive circuits. So I will see you in the next topic for the next video.